Thanks for joining me for part 2 of our trimester exam, final exam review. We are going to pick up where we left off. So we were talking about convection currents and movement of plates. So changes in temperature and density are what cause these convection currents. Let's move along to see how that looks, even in a smaller example. So we can have something like a fire. Fire puts out heat, and that heat can move to a place, can move to other locations, but it can be sort of absorbed by something like a pot, as we see here, and it's absorbed by that pot, or it's moved from the source, the fire, to the pot through radiation. So radiation is energy that's radiated or transmitted in the form of rays, waves, or particles. So the rays of heat, and this is when you go out in the summer to kind of sit in the sun, you say, I'm soaking up some rays. You are soaking up radiation from the sun. So that's the term radiation. Conduction is the direct touching of a hot substance, so heat transfer through direct contact, the transfer of heat or electric current from one substance to another by direct contact. So here, once that heat hits the pot is going to change temperature, and if your hand touches the pot, your hand will feel that burn because of conduction. So radiation takes the heat to the pot. The pot is hot, but it takes the heat to your hand through conduction, through direct contact. It is also conducting heat to the water. So the water molecules at the bottom of the pot are receiving heat through conduction. But those hot water molecules will start to heat up the water at the top, because as those molecules begin to increase in temperature, they will also change their density. So they will move up because less dense fluid molecules move upward, and when they move upward away from the heat source, they're going to cool down and they're going to sink because they're going to become more dense, and then we'll get this pattern of heating and cooling called convection, the transfer of heat through a fluid caused by molecular motion, and that fluid can be liquid or gas. Here we're looking at a liquid example, but we're going to also see examples of gas when we look at the atmosphere. Okay, wonderful. Those concepts are ones that you'll see multiple times on the exam, so I wanted to make sure that we review them. We also need to look at earthquake detection. So when earthquakes take place, what are the tools that we use to detect them? A, seismometers are the answer that we're looking for. And when we have information from 3 different seismic stations, so here it looks like is the place that the earthquake took place. And so a seismic station in Charleston, South Carolina can measure and say, okay, it took, and there's 2 different types of waves that this seismic station is going to be measuring, S and P waves. The P waves will arrive first, and then S waves will start to arrive, and based on the time in between when those waves arrive, we can make an approximation of how far that earthquake was from the station in Charleston, South Carolina. And we'll draw a circle saying we know it's so many miles away, but we don't know where along the circle that occurs. The same would happen at the next seismic station. The S and the P waves would arrive. The seismologist would say, okay, based on the time it took between the P waves arriving first and the S waves arriving second, the time tells us that the earthquake was this distance from this seismic station. And so you would form a second circle, and then the same thing for the third circle. If you only had 2 seismic stations, you can see here, if we look at just the red and the blue lines, they cross here and they cross here. So you wouldn't know which one was the location of the earthquake. But when we have 3 seismic station pieces of data, we can put all 3 circles and they will overlap in only one location. So there's only one place that these 3 circles meet, and that is called triangulation, or using 3 seismic stations to make those location information. How do we know, or what are these S and P waves, and how do we use them to know about the interior of the Earth? How do we know about the inner and the outer, the inner and the outer core of the Earth? How do we know what their consistency is? We know it because S and P waves have different characteristics, and they create something called shadow zones. So P waves can travel through any type of material, liquid or solid. And so we see here that if an earthquake occurred at this location, P waves could be detected all across the Earth. We get a shadow zone because when the P waves hit a liquid, and this outer core is liquid, they get deflected. So the light, or not the light, but the energy from these P waves is deflected. And so there's a part of the Earth on sort of both sides of where these waves start to come out that you won't be able to detect P waves, and we call that the shadow zone. The same is true for S waves, but S waves can only travel through solids. So as soon as they hit that liquid outer core of the Earth, they get deflected away and they're not able. So they create a different shadow zone pattern, or a different place where S waves aren't detected. When seismologists kind of put all this information together, compile all the data, we can understand about what part of the Earth is liquid and what part is solid, and it helps us understand the consistency of the interior of the Earth. Okay, let's move along to minerals. We talked about minerals because they are the ingredients that make rocks. There are 5 different properties of minerals that we look at to help identify them. The first is streak. Streak tells us information about that is more reliable than the color of a mineral, because streak is the powder that the mineral makes when it's scraped on a small piece of unglazed porcelain. So if you kind of scratch that mineral on the surface of porcelain, it will produce a color, and that color is more reliable than the color that you see by just looking at the mineral. That is because the color could, change based on factors like oxidation or the sort of light reflection. Luster is a description of how the surface of the mineral reflects light. So terms like glassy, metallic, shiny, those are ways that we describe the luster of a mineral, and they're also characteristics. So some minerals have a metallic look to them, and some minerals are dull, and that can help identify which mineral we're looking at. Cleavage is the way a mineral breaks, and it is used to help identify it. Hardness is how resistant the mineral is to being scratched, and I'll talk about the hardness scale coming up. And then special properties, so not all minerals have these, but some include radioactivity, some are fluorescent, some reflect light in different ways. So those are the properties of minerals that we look at. How do we determine if something is a mineral in the first place? Not all substances on our planet are minerals. In order to be a mineral, first they need to be naturally occurring. So they just exist in the earth. They're sort of created through natural earth processes. But they have to be inorganic. So they cannot be created, or they cannot be part of something that's living. So they are naturally occurring inorganic substances. They also need to be solid. So water would not count as a mineral. Water is naturally occurring. Water is inorganic. It doesn't contain carbon. It's just hydrogen and oxygen. But water is not solid, so it doesn't meet that criteria. It needs to have a regular crystal structure. That means if you kind of zoom in and look at the way the atoms are arranged in the substance, they form these regular patterns. So we can take a look at that in a sort of microscopic level. And then a definite chemical composition. So water, its composition is H2O. We said it's not a mineral for other reasons, but water does have a definite chemical composition, and the same is true for minerals. So for diamond, for talc, for galena, we can take a look and see what the mineral composition is or the definite chemical composition is. This is an example of a rock, granite, and it is not a mineral because you can see it's not consistent throughout. There's sort of different amounts and different consistencies of the chemicals that make it up. Moving along to the hardness scale. The hardness scale is just how soft or hard a mineral is compared to other things. And so we know that talc is the softest mineral and diamond is the hardest mineral. And so we can use these other kind of standpoints to compare things to it. We also know a fingernail is sort of like over a 2 on the scale. So a fingernail could scratch gypsum, but a fingernail couldn't make a scratch on calcite. And the same is true for pennies, steel, glass, and a streak plate. We have these comparison tools that we use to determine hardness. Thanks for watching part 2 of the video. We're going to continue on with part 3 in just a second.